Right guys, so for your exam on the subject of generators and sine waves, these are the key things you need to know. You need to know the laws of electrical induction, you need to know Fleming's right-hand rule, and you need to know how a sine wave is plotted. You need to know how a generator works to generate electricity to produce the sine wave, and you also need to know your sine wave quantities, okay, your sinusoidal quantities. So let's move on to next, which is electrical induction. So electrical induction, whenever a magnet moves in relation to a coil of wire or a magnetic field changes in relation to a coil of wire, a voltage is induced, and that voltage is described by the formula E equals BLV. So E is the EMF in volts. Okay, B, or beta, is our flux density in the Tesla. L is the length of the conductor, and that is in the meter. And V is velocity, the speed at which the coil moves through the magnetic field, and that is in meters per second. And on the right here we have got Fleming's right-hand rule, okay? Fleming's right-hand rule, and that is for generators, or generators, as I say, really annoyingly. Right, Fleming's right-hand rule. So the thumb indicates the direction of movement, okay? So that is the direction of which force is applied to the conductor. Your first finger, index finger, indicates the direction of the magnetic field. Okay, so it's the lines of flux, so those point from north to south. Okay, so that's the direction of the magnetic field. And then finally, your second finger indicates the direction of current. Okay, so if we put the actual values from the equation on there, so V, velocity, so the direction of travel, and this is flux density, okay, the magnetic field, and then this is the current induced, okay, the direction which current flows, and that is obviously down to our induced voltage. The amount of current flow depends on the induced voltage on the circuit. Right, next, how actually we generate electricity. So this circuit diagram here just shows a simple generator which consists of a magnet, permanent magnet, being rotated in respect of a coil. At this stage, the magnet is flat. There is no magnetic field, no lines of flux are crossing across that magnet. If I very quickly just draw you some lines of flux, remember they go from the North Pole to the South Pole externally, okay, and then move through. So at the moment those lines of flux are nowhere near the coil, and they're not cutting across the coil either. So if we rotate that magnetic field, if we rotate that magnet, and so it becomes vertical. It's very boring, but there we go, this is the way I've got to do it. And we rotate our magnet so that it is vertical, and there is our north, there is our south. Our lines of flux are now coming out, and they're cutting across that coil. Okay, so it's awful drawing, but you kind of get the idea. So as it rotates, the lines of flux rotate with the magnet, and they will cut through the coil, and that as they cut across the coil, they will generate electricity. So at present, we have got 0 degrees of rotation, so we'll mark this here as 0. If the magnet turns by 90 degrees, then the lines of flux will be cutting across the coil at maximum velocity and maximum strength, which means we get a maximum voltage induced. As we rotate further, the north will then come round to this side, and now we're getting flat, no voltage is being induced. as we rotate further, the north will come down to here, and now the south pole is cutting across, and that will change the direction of our current flow according to Fleming's right-hand rule for generators. And then can't continue rotating, and we come back to here. So we've done 360 degrees, which takes us back to zero, effectively. So what we can do, we can make a plot which indicates that at 0 degrees of rotation, we've got 0 voltage. At 90 degrees of rotation, we have got maximum voltage. 180 degrees of rotation, we're back to 0. 270 degrees of rotation, we have got maximum voltage. And then finally back to 360, again we're at 0 volts. If we join those together, we get a triangle, but that's not how it actually works, because the amount of voltage increases quite steeply at the beginning, and then it drops off as you get towards the top. In fact, this is described using the sine function. So V, okay, the V, and this is instantaneous voltage. Okay, the voltage at any one point is equal to V max, the peak voltage that you can get to, which is described by Fleming's by E equals BLV, multiplied by the sine of theta. Now theta is the angle of rotation. Okay, so you could take point at 90 degrees, and we'd have our whatever our maximum voltage is multiplied by the sine of 90, which is 1, so that gives us the full maximum voltage. If we take 45 degrees, we'll find that the sine of 45 is actually 0.707, which is kind of up here. Okay, so this means that what we get plotted, if we join all the dots together, is not a triangle, but actually this nice curvy shape, which I've drawn really badly, which is called a sine wave. Okay. So that's how a generator works. Spin a magnet in respect of a magnetic field. Spin a magnet in respect of a coil, and a voltage will be induced in that coil, and the voltage induced will be proportional to the sine of the angle of rotation multiplied by the maximum possible voltage you can have. So now we're going to move on to the sine wave itself. So sine waves have got 3 basic values that you need to be aware of. Might crop up in this exam. First of all, we have peak, and that is the maximum possible voltage you can have. V plus, you also have a negative peak. Okay, negative and positive voltages in sines are just as important. Okay, a positive voltage will hurt just as much as a negative voltage if you touch it. Okay, if you're in the middle at 0. So we got peak, positive peak, and a negative peak. Now that is not the voltage that you actually get out. When you look at your 230 volt supply that we might get from our wall socket, we will not get the peak voltage. That's not what we use when we're calculating how much current flows. What we use is something called RMS, which stands for root mean square, which is a mathematical way of getting something close to an average. Now, the root mean square is actually proportional to the individual values squared, finding the average of those squares, and then finding the square root of the average of the squares. So that's quite a rigmarole. Okay, so you're not expected to have to calculate that. So what we find is that the RMS value is equal. Sorry, I'm just going to change colour because I know that blue doesn't show up. RMS is equal to the peak voltage multiplied by 0.707, which you'll remember was actually the sine of 45 degrees. Just happens to be that value. Peak, if we do the opposite, peak is equal to RMS times 1.41. It just is. Those are just those values. They're just factors. There's no unit measurement associated with those. They just are. And then finally, you have the average. Now, the average voltage is actually a little bit less than the RMS. Okay, average is equal to peak times 0.637. Okay, and then I think that the opposite is 1.1, that RMS is average times 1.1, which is sometimes known as the form factor, but I doubt that will come up in the exam. So the key things, peak and RMS are different. The peak is the maximum that we get to. The RMS is the effective voltage. It will provide the same amount of heating in an equivalent voltage DC circuit. If you've got 100 volts DC, that does the same amount of work as 100 volts AC RMS. We don't use peak, we use RMS. So let's go back to our beginning. So you need to know about induction. So induction, E equals BLV, and you use Fleming's right hand rule. Okay. So Fleming's right hand rule, thumb is our force, okay, the direction, velocity. The first finger is our magnetic field. Our second finger is the induced current flow. Okay, sine waves are produced by generators. A generator is effectively a magnet rotating with respect to the coil, and it induces a voltage in that coil. The induced voltage will be a sine wave. So remember, sine wave is our nice, smooth wave. Okay. Sinusoidal quantities consist of peak voltages, RMS voltages, and average voltages. And a sine wave is what happens if we take the angle of rotation, theta. Okay, remember that's the Greek letter theta there. Take the angle of rotation and we multiply it by take this sine of the angle of rotation and multiply it by the peak voltage, and that gives you your instantaneous value, which then plots your sine wave. There we go. Good luck with the exam today.